This is Unit 10, Example 1, constructing a sampling distribution with SAT scores. The National College Athletics Association, NCAA, requires freshman Division II athletes to score at least 820 combined total on both sections of the SAT exam. The scores of the 1.5 million high school seniors who took the SAT last year were approximately normal, with mean 1,026 and standard deviation 209. Question A asks, how many standard deviations away from the population mean is an SAT score of 820? Use the z-score formula for the proportion to solve. Our z-score formula is that the number of standard deviations z equals the value we're looking at, x, minus the mean divided by the standard deviation. And so in this case, we're looking at an SAT score of 820, so we're imagining one student with a score of 820. So in the fraction, we do the numerator calculations first. So we're going to first calculate 820 minus 1026. That's why I have this in parentheses. And then we're going to divide by the standard deviation 209. So if we work that out on our calculator, we get negative 0.986, or approximately negative 0.99. So right around one standard deviation below the mean. This is a negative z-score because our value 820 is less than the mean of 1026. So we can say the z-score formula tells us that we are negative 0.99 standard deviations from the mean. Now in question B, we're told at Deer Valley High School in Antioch, there are 36 seniors on the basketball team. Suppose we take a simple random sample of size 36 from the population of all high school seniors, find the sample mean x bar for each sample, and then repeat this many times and plot the sampling distribution. Since our sample size is greater than 30, we're confident that the distribution is going to be fairly normal. So a sample size of 30 is our cutoff to assume that the distribution will be close to normal. Where is the center of this sampling distribution? How many standard deviations away from the sample mean is an SAT score of 820? Use the z-score formula for the sampling distributions to solve. So the first thing to establish is that the center of the sampling distribution is the same as the center of the population distribution. So we'll be working with the same center, 1026. If you imagine our bell curve, it's still going to be centered at 1026, just as if when we had one student. So now we're thinking about the sample mean being 820. So this is saying all 36 students, when we average their samples, the mean score would be 820, not just one student. So following the z-score formula, because we're working with 36 scores, we're going to take our standard deviation and divide it by the square root of 36, which is 6. So in our numerator, we're still calculating 820 subtract 1026, and then we're dividing by the standard deviation 209 divided by the square root of 36. So that will work out to be 209 divided by 6, and then we end up with negative 206 divided by 34.83333, and so we end up at negative 5.9139. So our z-score formula is telling us we are negative 5.9, or almost negative 6 standard deviations from the mean. So this is a very extreme outlier. So what this is saying is, while it may not be that unusual for one student to have a score of 820, what we looked at in Part A, it's extremely unusual for the average of 36 students to be a mean of 820. So this is more than 5 standard deviations away from the mean. It is unusual for the average of 36 students to be 820. So again, it might be reasonable to have one random student have a score of 820, but if you randomly sampled 36 students, it would be very unusual for their average score to be 820. This is because we expect average scores to be, when you have a large group, to be closer to the mean, which is 1026. Question C asks us to find a 95% confidence interval for the SAT scores of all high school seniors last year. So we're working with the population for all high school seniors, and so our standard deviation is the 209 population standard deviation. And so our upper bound is our mean plus 2 times 209, and that is 1,444 for the SAT score. And our lower bound is 1,026 minus 2 times 209 is 608 for our SAT score. So remember, this is 95% confidence, so we say it's around 2 standard deviations. So with 95% confidence, we can predict that the true mean SAT score for all high school seniors is 608 to 1444 for their SAT score. This is quite a big range, and again, that's because we have this high 95% confidence, right? This is a large range for the SAT scores if we know the average is 1,026. Part D says find the 95% confidence interval for the sampling distribution of SAT scores of high school seniors when n equals 36. So now we're saying if instead of looking at the whole population, we look at 36 students in a random sample. So we're looking at a smaller group, so we have less range for where we think the true mean is going to lie. So when we do our calculations, our standard deviation is sigma 209 divided by the square root of 36, or that'll reduce to be 209 divided by 6. So we use here for our sampling standard deviation 34.833333. And this is because we're working with a random sample of 36 students, not the entire population. So a smaller group of students, we expect that's going to shrink or compress our standard deviation. And we see when we do 1,026 plus 2 times 34.83333, we get the upper bound as 1,095.666 for the SAT score. I don't think SAT scores come in decimals, so this would probably, in reality, in a study, be rounded up to, say, 1,096. Similarly, the lower bound by the same calculations, but with subtraction of 2 times the standard deviation from the mean, works out to be 956.333. So in reality, in a study, this would probably be rounded down to, say, 956 is the lower bound. And so we can say with 95% confidence, if we have a sample of just 36 students, then the true mean of those 36 students, based on what we know about the population, we expect to lie between 956 and 1,095.666 or 1,096 if we round up. So again, we're never 100% sure, but 95% confidence is pretty sure. So why is this confidence interval smaller than the one for the entire population? So if you think about it, we're working with a sample and we're taking the mean of that sample. So when we do the mean of the sample, that's going to give us values closer to the center. And if we take very many sample means, we expect our data to lie much closer to the population mean 1,026. So because we're dealing with sample means, we're going to end up with a narrower confidence interval because we're taking all this data, finding the mean or the average from the 36 students, and then plotting it. And if we do this very many times, we expect their true mean to lie between 956 and 1,095 or 1,096 if we round up. Example 2 is a vocabulary check. So question A says, in a matched pairs experiment, subjects pushed a button as quickly as they could after taking a caffeine pill and also after taking a placebo pill. The mean pushes per minute were 283 for the placebo and 311 for caffeine. Is each of the bold numbers a parameter or a statistic? So both of these numbers from the placebo and the caffeine group come from the experiment, so these are statistics. The sample mean for calculation purposes in a matched pairs experiment is calculated by subtracting the caffeine value and the placebo value. So the placebo value is used as a baseline, and then they would say how far away is the caffeine group in terms of mean pushes per minute. They call this a matched pairs experiment because it's the same subjects pushing the button, so they're comparing them to themselves. And so they're looking at the same person after taking a caffeine pill and after taking a placebo pill. Question B says the Bureau of Labor Statistics announces that last month it interviewed all members of the labor force in a sample of 60,000 households. 8.9% of the people interviewed were unemployed. So we want to know, what is this bold font number? So it's 8.9% of the people interviewed, meaning the people in the sample of 60,000 households that they were using to try to predict all members of the labor force. So this is a statistic because it comes from sample data. Question C. A study of voting chose 663 registered voters at random shortly after an election. Of these 663, 72% said they had voted in an election. Election records show that only 56% of registered voters voted in the election. So the bold font number is the 56% from election records, and that's a parameter because it's data about the whole population. Election records show data about everyone who voted. Question D says scores on the mathematics part of the SAT exam in recent year were roughly normal with mean 515 and standard deviation 114. So if we imagine the graph, the center will be at 515 and each standard deviation will be 114 points. You choose a simple random sample of 100 students and average their SAT math scores. If you do this many times, the mean of the average scores will get close to what? So here we're taking simple random samples of 100 students, adding up all their scores, dividing by 100, taking the mean, and then we're going to do this for many, many, many groups. So this is the idea of the sampling distribution. So we expect from the law of large numbers that if we have a large number of data, our means are going to get close to the population mean. So we expect the mean of the average to be close to 515, right? If you're taking many, many random samples, averaging their data, and then repeating that, you're going to get close to the population mean. This is by the law of large numbers and the central limit theorem. Question E. Scores on the mathematics part of the SAT exam in a recent year were roughly normal with mean 515 and standard deviation 114. So we're talking about the same data as in the last question. You choose a simple random sample of 100 students and average their SAT math scores. If you do this many times, the standard deviation of the average scores you get will be close to what? So this is that formula that when we're taking a random sample of n students, in this case n is 100, that our standard deviation shrinks because our sample is no longer the whole population, it's a subgroup of the population. So the formula is sigma, which is 114, the standard deviation, divided by the square root of n, which is the square root of 100. So if we work this out, we know the square root of 100 is 10. So 114 divided by 10 is 11.4. So if you imagine the normal distribution graph, it's going to compress with a smaller standard deviation because we're looking at a smaller group of students. Question F. The number of hours a light bulb burns before failing varies from bulb to bulb. The distribution of the burnout times is strongly skewed right. So skewed right, we know that means it's going to have a tail to the right, meaning a few light bulbs last a very long time. Most light bulbs will burn out around the average burnout time. So the central limit theorem says what? So if we read through the following choices, we find that choice C agrees with what we know the central limit theorem says. The average burnout time of a large number of bulbs has a distribution that is close to normal. So even though the starting graph is skewed to the right, if you do averages of different numbers of bulbs and repeat that many times, we're going to get close to normal in their distribution. So imagine taking the sampling distribution. You're going to do a random sample maybe of 100 light bulbs, take their average, take a random sample of another 100 light bulbs, take their average, and we're going to get the sample means, right, the sample averages are going to form a distribution that is close to normal. So even though the original distribution was skewed, when we pull out samples, take their averages, we end up very close to normal in the distribution. Example 3, applying the law of large numbers. According to the law of large numbers, which we saw back in Unit 7, if we keep on taking larger and larger samples, the statistic x bar, so that's the mean or the sample mean, is guaranteed to get closer and closer to the parameter mu, that's the population mean. If we are able to keep measuring more subjects, eventually we will estimate the mean value very accurately. So question A tells us there are twice as many slot machines as bank ATMs in the United States. Modern slot machines are video games with flashy graphics and outcomes produced by random number generators. Gamblers still search for systems in hopes of winning big, but in the long run, the law of large numbers guarantees the gambling house 5% profit. A friend who knows you are taking a statistics class text messages you that she has just won $100 at a slot machine in Reno. Should your friend spend her $100 playing more slot machines? Explain the best advice to text back. So we know from the law of large numbers in the Unit 7 vocabulary that when we have a large sample, the statistics are closer to the actual parameters. The parameter in this situation are 5% profit for the gambling house and 95% return on the money spent for gamblers. As your friend spends more money gambling, she will get closer to 95% back of the money she spent gambling. If your friend spends her $100 playing more slot machines, we expect that she will earn back $95 and the gambling house will make $5. So that's not a good payback for her. She's got $100 in her pocket. So the best advice you should text back to your friend is to recommend your friend quit gambling while she is ahead. Question B is about the idea of insurance. So the idea of insurance is that we all face risks that are unlikely but carry a high cost. Think of a fire destroying your home. Insurance spreads the risk. We all pay a small amount, and the insurance company policy pays a large amount to those few of us whose homes burn down. An insurance company looks at the record for millions of homeowners and sees that the mean loss from a fire per year is mu equals $250 per person. So this is because many of us have no fire loss, but a few lose their homes, so the $250 is the average loss. The company plans to sell fire insurance for $250 plus enough to cover its costs and profit. Explain clearly why it would be unwise to sell only 12 policies. Then explain why selling thousands of these policies would be a safe business. So if you sell only 12 policies, there would not be enough income to cover the cost of even one fire. If thousands of policies are sold, there's enough income to cover the cost of a fire. The insurance company should make sure to sell policies in many different cities in case of disaster. So there is a famous example of Farmers Insurance Company that sold many policies in Oakland and then nearly went bankrupt after the Oakland Hills fire in 1990. So insurance companies want to avoid having all of their policies in the same area because if there's a large fire there, then they may not have enough to cover the average loss from the fire. So what the law of large numbers is saying is if we know the risk of a fire, we can spread that around by selling very many policies to cover the cost of a fire.